Okay. So the first speaker is Hussien Othman from Ben-Gurion University. He's a student of Amos Bainer, and he's going to talk about evolving Ramp secret sharing schemes. So Hussein, the stage is yours.
Thank you. Hi all. I am Hussein. I will be talking about evolving Ramp secret sharing schemes, joint work with Amos Bima. In this talk, we will start by recalling secret sharing schemes. Then we will define the model of evolving secret sharing and present previous results on secret sharing. And then we will present our results in evolving Ramp secret sharing schemes. And then we will briefly describe our constructions. And at the end, we will summarize and discuss several open problems in evolving secret sharing. So secret sharing schemes were first presented independently by Shamir and Blakely in '79 for the threshold case, and by Eto Sesto Nichizuki in '87 for the general case. In secret sharing, there is a dealer who had a secret S. There is a set of participants whose number is known in advance. Now, the dealer applies a function on the secret, and it generates in shares and gives each party a share. We define an access structure as a subset of parties, as a collection of subsets of parties, and we say that the secret sharing scheme realizes the access structure gamma if the following two conditions hold. The first condition is correctness. In correctness, we require that any set that is gamma should learn the secret. And the second requirement is security. And we require that any set that it's not in gamma would get no information about the secret. And we say that this is an authorized set. And the sets that are in gamma, we say that they are authorized sets. In this talk, the secret is only one bit unless we mention otherwise. Next, we will present Shamir's secret sharing. Shamir's secret sharing realizes the threshold access structure. In this access structure, this access structure contains only the subsets of size at least T. The scheme is very simple. The secret is chosen from a field, a finite field with if P where P is a prime number that is greater than n. The dealer it chooses T minus 1 random elements R1, R2, and so on from the finite field and defines a polynomial Q. Where the coefficients of Q are the random bits, and the polynomial is of degree P minus 1, and now the set the value of the point 0 on the polynomial. Now the dealer gives each party here, party J gets the point Qj, and by Lagrange theorem, we can prove that any T parties can find the Q and reconstruct the secret, and any T minus 1 parties cannot find the Q and not learn anything about the secret. The share size in this scheme is the share of each party is one field element, and the secret is also one field element. When we take P, which is the minimal prime number that is greater than n, then we get the share size order log n. Next, we will define secret sharing presented by Blakely and the models in '85. In RAM secret sharing, there are two parameters, P and G, such that B is smaller than G. And we say that B stands for bad and G stands for good. In ramp, we have the correctness requirement in ramp, like in the threshold, we every set of size at this B should secret, and in security, every set of size less than B should get no information about the secret. And now in ramp, with difference from a threshold, we introduce a gap. We introduce a gap such that any set of size between B and G, we don't care about it, and anything might happen for this set. Next, we'll present a simple ramp secret sharing scheme that is based in Shamir's scheme. In this scheme, the secret is G minus B field elements, and now we define a G minus B points, where the value of point n plus 1 is 1, the value of n plus 2 is 2, and so on. The value of n plus G minus B is G minus B, and these points are the secret. Now, like in Shamir, we construct a polynomial of degree g minus 1 and give its party a share, where the share of party pi is a qi. The points should not be anyone. The points given to the parties should be any point from the defined g minus b point, and the polynomial should pass through this g minus b points. So for correctness, like in Shamir, we can, by Lagrange theorem, we can prove that every G parties can reconstruct Q and learn the secret. The share size in this scheme is like in Shamir is also one field element. However, the secret is now a G minus B element, and therefore RAM secret sharing is more efficient than Shamir's scheme. In secret sharing, there is one theorem that we will use in our constructions. It says that for every p smaller than half, there is a RAM secret sharing scheme with the security parameter bn and correctness parameter n over 2, and the share size of each party is order 1. So RAM secret sharing are used for various applications. They are used to construct efficient MPC protocol, and this due to the fact that the share size in RAM secret sharing is the same like in Shamir's scheme, while the secret is longer. They are used to implement the broadcast encryption, the error decodable secret sharing, and many various other applications. So now we are ready to present the model of evolving secret sharing. This evolving secret sharing was introduced by Komarditsky or Yogev in 16. In evolving secret sharing, like in the standard secret sharing, there is a dealer who holds a secret S, and now. Excuse me. Okay. And now, unlike with difference from standard secret sharing, in evolving secret sharing, we don't know the set of parties in advance, and even we don't know their number. So there is no fixed upper bound on their number. Parties arrive one after the other, and when a party arrives, the dealer gives it a share. Now party P1 arrives, it gets a share. The second party arrives, gets a share, and so on. P million, 1 million arrives, it gets a share, and this continues forever. An important requirement in evolving secret sharing that with shares are not updated later. That means that the share that the party gets on his arrival should be used in any time in the future in order to learn the secret. So an access structure in the evolving secret sharing contains a collection of a finite set of parties, and for correctness, we show that every set that is in gamma should learn the secret, and any finite set that is not in gamma should not get any information about the secret. So as we know that in traditional secret sharing, the number of parties should be known in advance in order to learn to construct the scheme. Like in Shamir's scheme, we had to know the number of parties in order to choose the finite field that is critical in the construction. And now, since in evolving, when we look at the model when the number of parties is unknown, then we cannot use the traditional secret sharing. So a trivial solution could be that update the shares of all the parties periodically in some points. This can be very costly, and each update can be very costly when we have a large number of parties. The model of evolving secret sharing is also important, even if we have an upper bound on the number of parties. For example, if we know that in the scheme can join at maximum 1 million parties, but in real time arrive only 10 parties, then we want to give this 10 parties short shares compared to what would they get if all the 1 million parties participate. Next, we'll present a simple scheme for threshold 2, evolving to threshold 2. In this scheme, any two parties should learn the secret, and any single party should get no information about the secret. The scheme is very simple. When party P1 arrives, it gets a share. A dealer gives it a new random bit R1. When party P2 arrives, the dealer gives it two random bits. The first one is R1 XOR S. From this bit, he can learn the secret joining with P1 and gets a new random bit R2, which is used in order to learn the secret could join in with future parties. So party T gets T random bits. The first T minus 1 bit. The first T minus 1 bits are used to learn the secret from the previous parties, and the new random bit R2 is used to learn the secret with joining with future parties. So the correctness, in order to prove correctness, if we look at the two parties, Pi and Pj, such that I is smaller than J, then Pi has the random bit Ri, and Pj has Ri XOR S, and therefore XORing these bits, they get the secret. For security, notice that every single party gets independent random bits, and from these bits, he cannot get any information about the secret. The share size of party T in this scheme is order T, and this is not the best known in threshold 2 scheme. Next, we present the previous result in evolving secret sharing. So there is a scheme that realizes the K threshold secret sharing for any constant K, such that the share size of party T is K log T. When K is 2, the scheme is optimized, and the share will be order log T. And there is also a scheme that realizes the general axis structure, general evolving axis structures with a share size T2 to the T minus 1 for party T. Next, we'll present evolving alpha T threshold. Now, the threshold is not a constant, it's a function alpha T. So we have a function evolving.
Hussein, can I ask you a question? When you mentioned the previous ones, so when I want to generate, I don't know, the T share, do I have to work in terms of computational complexity linearly with T, or maybe more than that, or can I, like the share size was sublinear in T, right? So can I also work sublinear in T?
the share size.
Not this one. No. Go to the next one. The more sophisticated things that you mentioned. Like you had the log T thing.
This.
Right. Yes. So can I hope to work with this complexity or any complexity which is sublinear in the number of parties when I get to the Th party?
The best we know is the K log T. There is no problem if we can get rid of the factor K in this share size.
No, I'm thinking about K as constant. Think about K equals 2. So I'm just asking about the computational complexity of generating the shares.
The optimal share size is log T when we look.
Yeah, but I'm talking about the computational complexity of the dealer, not the share size.
The computational complexity of the dealer?
Yes. I'm the dealer and I want to generate the 100th share. Like, do I have to work linearly with 100?
We didn't study computational complexity of the dealer.
Benny?
Yes.
The work of the dealer will be proportional to the share size.
To that?
The work of the dealer will be, in this scheme, will be K log T.
I see. Okay, good. Thank you.
So we have the evolving threshold function, which alpha, which is a non-decreasing function from n to n. And now, for example, we look at alpha t equals t over 2. This is it's called the majority function, and we will use this function to present our results for simplicity. And now, if there are two requirements, the first requirement is the correctness. In correctness, we say that a subset of parties A can learn the secret if there is a prefix j such that A contains at least alpha j parties from the prefix of the first j parties. So if we look, for example, at the set P3, P5, P6, then A contains the 3 parties from the prefix of the 6 parties, and this equals to alpha 6, and therefore this set can learn the secret. If we add party P13, also this set can learn the secret from monotonicity. For security, we require that that a set cannot get an information about the secret if for every j it contains less than alpha j parties from the prefix of the first j parties. So if we look at P3, P6, this set is unauthorized since it contains, if we look at the prefix of the first 6 parties, it contains less than 3 parties. It contains only 2 parties, which is smaller than alpha 6. And if we take a look at the prefix of the 3 parties, then it contains only 1 party from it, and this is smaller than alpha 3. And we can see that this holds for every prefix, and therefore the security requirement holds, and this set should not get any information about the secret. For alpha T threshold secret sharing, there is a scheme that realizes this axis structure with the share size 2 to the 4 log T for any function alpha T. So now we'll present our results in evolving ramp secret sharing. So we know that the evolving alpha T threshold secret sharing schemes require share size 2 to the 4 log T. We know that the standard threshold schemes have short size of order log T, while the standard ramp schemes improve this share size. And for example, if we look at ramp schemes with parameters over 4 and n over 2, and the share size is order 1. Motivated by these results, we question if we can reduce the share size also in the evolving setting. So next we'll define evolving ramp secret sharing. So we have two parameters. T/2 minus ft is for the correct for security, and T/2 for correctness. We use it. We present our result only for T/2, and but they apply for every function for every a constant fraction of t, not only for T/2. We call ft the gap. So for example, if we look at the T/2, T/T RAM secret sharing, ft the gap is T/4. And now the requirements, the correctness requirement is the same requirement in alpha T threshold. We say that the set can learn the secret if there is some prefix j, such that A contains at least half of the parts from this prefix. So P4, P5, 6 can learn the secret, the same since it contains half of the parts from the first 6 parts, and P13 can learn the secret from monotonicity. Now for security, we require that a set cannot get any information about the secret if for every prefix j, it contains less than j/2 minus fj parts from this prefix. This different from the security requirement in alpha T threshold, where we require that it contains less than j/2 parts. So now we allow a gap of fj. For example, if we look at the P at P16, this is an authorized set, since from the prefix of the first 16 parts, A contains only 2 parts, while quarter of 16 is 4. And from the prefix of 8 parts, it contains only 1 part, while a quarter of 8 is 2. If we look at P6, P7, P8, this not is okay. So A contains 3 parts from the prefix of the 8 parts, which is greater than 2, that is required in the security requirement. Therefore, this set is not unauthorized. Also, this set not authorized, since in each prefix, from each prefix, it contains less than half of the parts. So next we'll present our contributions. Our main result is to construct efficient evolving ramp schemes. So we prove the following results. When we look at a gap, a big gap, which is a constant fraction of t, then we get a secret sharing scheme with share size order 1. When we look at the gap, with smaller gap, which is t to the beta for any beta between 0 and 1, then we get share size t to the 1/beta minus 1. Now, if we look at beta, which is half, the share size is order t, which improves the share size in the alpha T threshold secret sharing. However, if we look at beta, which is fifth, the share size will be t to the 4, and this is not efficient compared to the alpha T threshold, which also require t to the 4. Therefore, we present our third results, in which we reduce the share size into t to the 4 minus 1 over log square 1/beta. This is asymptotic share size. This is an asymptotic share size. If we take a particular beta, the share size will be much better. For example, for beta, which is 1/5, the share size will be t square. Okay, so now we'll present our constructions. As a warm-up, we will start by presenting ramp secret sharing with gap t when the security parameter is t/8. So in this scheme, we divide the parts into segments. The first segment contains 2 parts. The second segment contains 4 parts. The third one contains 8 parts, and so on. The 11th segment contains 2 to the L parties from 2 to the L minus 1 until 2 to the L plus 2, 1 minus 2. And now, now we share the secret by Shamir's scheme in each segment. So with threshold, which is a quarter of the parties. So in the second segment, for example, we share it by 1 out of 4, in the third by 2 out of 8, and so on. In the Lth segment, we share the secret by 2 to the L over 4 out of 2 to the L. In order to prove correctness of this scheme, we should be sure that for any authorized set contains at least a quarter of the parties of some segment. So, for example, if we look at authorized set that ends in party PJ, then since this is an authorized set, it contains at least a J over 2 parties. And now, if we look at the last party in the up to the before the Lth segment, which is party 2 to the L minus 2, then if there is a segment that this set contains a quarter of the parties of it, then we are done. Otherwise, we can conclude that the number of the parties in the set up to party 2 to the L minus 2 is less than 2 to the L minus 2 over 4. And therefore, since the number of parties in the authorized is at least J over 2, we get that the number of parties in the set from the Lth segment is at least J over 2 minus 2 to the L minus 2 over 4. And since J is greater than 2 to the L minus 1, then we get that it's greater than 2 to the L over 4, which is the required threshold in order to learn the secret in the from the Lth segment. The share size in this scheme is orderly log T, since each party gets one share of Shamir's scheme, where each scheme is among order T parties. So we got a share size order log T, and we want to reduce this share size into order 1, like in standard secret chaining. So recall that we said that in standard ramp schemes, there is it can be realized with the share size order 1. So now, instead of sharing the secret by Shamir's scheme, we share it by a ramp standard ramp secret sharing in each segment. So with parameters with correctness parameter 2 to the L over 4, which is the same threshold that we used in Shamir's scheme, and now we allow a gap of 2 to the L over 9, and since we allow a gap in the security requirement, the security requirement will still hold in this case. Now the share size, since in RAM the share size is order 1, then we get share size order 1 for this scheme. So we show this scheme for T over 8, and we can generalize this scheme for every gap which is a constant fraction of T, and get share size order 1. So in the rest of this talk, we will construct schemes for smaller gaps than a constant fraction of T. We will look at the gaps which are function to T to the beta for any beta between 0 and 1. We do this in 2 steps. In the first step, we reduce the problem of involving RAM secret sharing into the problem of realizing finite access structures. So we show how from schemes that realize the finite access structures, we can get an evolving RAM secret sharing. And in the second step, we show implementation of schemes that rely on these finite access structures. And we do this in two techniques, in the segments technique and in the tree technique.
Hussein, can I ask a question before you start with this?
Yeah.
So if you look inside the construction that you just showed us, like in each block you use a ramp signature and write out of the box, and these things, the constructions that I'm aware of are based on just the random linear codes of appropriate dimensions. So it seems to me that you can just look at the whole construction if you open up the ramp schemes for each block, just as a sequence of random codes of appropriate length. So I wonder, did you try to analyze the whole thing directly just by looking at these matrices? Like maybe it will give you something more smooth because like just look at everything in encoding, look at everything under coding terminology. Because you just stack one over the other sequence of generating matrices of different dimensions. These are all these ramp schemes, basically.
Excuse me, I didn't understand the question.
So you cited Goldwasser et al. That implement these ramp schemes, right? The O of one ramp schemes. And if you look into the construction, this is basically a random generating matrix of a code, of a linear code.
Okay.
So you could just, if you open up this abstraction of ramp schemes and look at your construction, I think that you will see that you will basically concatenate many matrices, one over the other, of different dimensions. So I wonder, did you try to analyze it directly in these terms?
We didn't analyze. We used it as a black box.
I see. Okay, because there are constructions like in coding theory. I think that this corresponds to weightless codes, and there are ways to look at these things and analyze them. So I wonder whether you could just get a better analysis by looking at this like this.
Benny, what do you mean by better analysis? The size of the shape, or the one? What do you want to optimize?
I think that it will be smooth, right? I mean, first of all, I think that here you basically commit to this quarter, for example, right? To this fraction. And if you look at this continuously, this is just a long list of matrices, and you could later parse it the way you want, right? So maybe you will get something more universal in terms of the parameters of the ramp schemes. Also, I don't know, like the constants also matter, I guess.
So we did try to optimize the constant, but I think it's crucial that, at least it's crucial that we do independent sharing. And,
okay, it will be independent. Each row of the matrix will be independent, right? I mean, but okay, maybe I missed something here.
No, but in each matrix, you share the secret independently.
Right.
And I think this is crucial, and I don't think you can use one sharing from one scheme to use it for the next scheme.
I see. Okay, the randomness for, okay, that's a good answer. So you're saying the randomness for each the block is fresh. So it's just multiplying it by a single matrix, You use a different randomness for each thing.
Yes.
Okay, good. Okay.
Okay. So and now we'll present the reduction to finite access structures. So we define the access structure gamma T, which contains all the parties from party ft over 2 until party 2t. The gamma T it depends on ft, and we define this for every t. Now we say that a secret can learn the secret. A set can learn the secret if the following two conditions hold. The first condition is that there is some j such that j over greater than t. That means that the set ends in party pj such that pj comes after pt. And now This means that we are interested also only in authorized sets that end between T and 2T. And now we say that the second condition is that the set should contain at least J over 2 minus Ft over 2 parties from Ft over 2 until Pj. For security, this is the same requirement like in evolving ramp. So we require that for any J, the set contains less than J over 2 minus Fj parties from Ft over 2 until Pj. So since this is the same security requirement like in evolving ramp, then we get that any unauthorized set in evolving ramp is also unauthorized in gamma T for every T. Okay, so next we present the risk reduction. So our goal is a given scheme that by T that relies gamma T for every T, we want to construct a ramp secret sharing, evolving ramp secret sharing with gap T to the beta. The scheme is simple. For every L, we run the scheme pi with T2 to the L, and now party Pj gets shares from every T such that from L every L such that it is among gamma 2 to the L. That means for every J such that J is between F2 to the L over 2 and 2 to the L plus 1, which are the parties of in gamma 2 to the L. For example, if we look at if T equals T over 8, then the first, gamma pi 16 is among P1 to P32. Pi 2 to the L is among 2 to the L minus 3 until 2 to the L. Pi 2 to the L plus 1 is among 2 to the L minus 2 until 2 to the L plus 1, and so on. So we can see that party to the L minus 2 gets shares from pi 2 to the L plus 1 and pi 2 to the L, but doesn't get shares from any other scheme, not from pi to the L plus 2 or pi 16 or other schemes. So in order to prove the correctness of this scheme, we want to prove that given an authorized set in evolving ramp, then it can there is at least one pi 2 to the L for some L that realizes it. So if we consider an authorized set that ends in party Pj, then there is some L such that it's J between 2 to the L and 2 to the L plus 1, and for this L we show that the pi 2 to the L accepts this authorized set. So the scheme starts from party F2 to the L over 2, and now since this is an authorized set in ramp, then it contains at least a J over 2 parties, and now it contains at most F2 to the L over 2 parties from the first F2 to the L over 2 parties, and now hence it contains at least J over 2 minus F2 to the L of 2 to the L over 2 parties from the parties F2 to the L over 2 until Pj. And by the definition of correctness for gamma 2 to the L, we get that this set learns the secret from pi 2 to the L. Security, it follows by definition, as we said, every unauthorized set in evolving ramp is unauthorized in gamma T for every T. So now we'll present a scheme that realizes gamma T when the gap is square T. We said we show this scheme for square T, but also it applies for every function. So we do this by the segment technique. So we have the part is square t over 2 until 2t. And now we define segments. So the first segment is from square 2 over 2 t until part t plus square t. The second segment is up to t from the beginning until part t plus t square t. That means that in each the difference in each segment is each time we add square t parts, and so on until we get the last segment, which is from the first party until the last party. And now in each segment, we share the secret by Shamir's scheme with a threshold. And in each segment, the threshold is increased by square t over 2. So in order to prove correctness, we show an example for a set authorized set that ends in party bj, such that bj is in the between t plus square t and t plus 2 square t. And now, since this is an authorized set in gamma t, then it contains at least j over 2 minus square t over 2 parts. And since j is greater than t plus square t, then it is greater than t plus square t over 2 minus square t over 2, which is exactly the threshold that is required to learn the secret. And this idea we can generalize for every segment, for every authorized set. So the share size in this scheme, as we have square t segments, and in each segment we have order t parties, and we share the secret by Shamir's scheme, then the share size of party t of each party is square t log t. And if we represent the share size by the index of the party, since the smallest index is square t over 2, then we get share size order j log j for party pj.
So, Hussein, please try to finish in 5 minutes, okay?
When we use the reduction, we get evolving gram with share size j log square j, since each party is among log j schemes. So in this scheme, the first party gets shares for every segment, and therefore for a small beta, the number of segment is big, and this will result in big share for a small beta. And the solution is to use trees. So in trees, we generalize the idea that used to construct evolving threshold secret sharing. So if we look now at beta, which is t to the quarter, we define two layers, which is from 2 to the quarter over 2. The first layer is 2 to the quarter over 2 until square t, and the second is from square t until 2t. And now we define a set, okay, so now for every such C, we choose a random element, random bit RC, and we shared RC among the parties of the first layer by some threshold, and then we share RC XOR S by the first scheme. So we define segments where with gap 2 to the quarter, the difference between the segments is 2 to the quarter, not the square t, and do the segment like in the first scheme. And now, given an authorized set, it should learn RC from the first layer and RC XOR S from the second layer. So as I don't have time, I will skip the details. So as a summary, we introduced and constructed efficient evolving gram secret sharing schemes. When the gap is big, which is a constant fraction of t, we get share size order 1. when we look at gap, which is 2 to the t to the beta, where beta is between half and 1, the share size is a t to the 1 over beta minus 1, and we get this by segments technique. For when beta is between 0 and half, we get share size 4 minus 1 over log square 1 over beta, and this is by the tree technique. We showed the scheme for the beta, which is 1 over 4, and when beta is smaller, then we will need more layers in the tree. For optimal beta, we show that to get the optimal share size, we showed that we need at most log 1 over beta layers. So next we open problems. So we know that evolving alpha T threshold secret sharing, the best non-upper bound is requires the share size T to the 4. So we ask if we can improve this share size, motivated by the fact that in non-evolving the share size is log T. And we ask also if we can improve a non-trivial lower bound on this access structure. So we presented evolving ramp secret sharing, and we ask if we can improve our scheme or improve lower bounds on evolving ramp secret sharing. Another interesting problem is to consider prove lower bounds in a general evolving secret sharing, as evolving secret sharing is considered to be harder problem than the standard setting. Then proving lower bounds could be easier. Okay, thank you.
Thank you. Any questions? Okay, yes, Benny Applebaum?
No. It wasn't.
You were clapping your hands. Yeah, I thought you were.
I'm trying to be virtual.
Okay, so I'm pausing the recording now.